Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be going over material for your online Math 200 class from Chapter 12, which is just about some additional inferential procedures that we can perform. So we're going to start with section 12.1, which goes through the goodness of fit test. So first I want to talk about some characteristics of the chi-squared distribution. The first characteristic is that it's not symmetric and its shape depends on the degrees of freedom, just like the student's t-distribution. As the number of degrees of freedom increases, it becomes more nearly symmetric, and the values of chi-squared are non-negative. That is to say that the values of chi-squared are greater than or equal to 0. So if we take a look at our chi-squared distribution for various degrees of freedom, we'll see that as we have a larger number of degrees of freedom, just like it says here, it becomes more nearly symmetric. So degrees of freedom of 30 is this purple one here. This is much more symmetric than, for example, degrees of freedom of 5, which looks something like this. So a goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So let's first talk about expected counts. Okay, so let's suppose that there are n independent trials of an experiment with at least 3 mutually exclusive possible outcomes, which we would denote like from 1 all the way to k. P1 is going to represent the probability of observing the first outcome, and E1 represents the represented expected count of the first outcome. P2 is going to be the probability of observing the second outcome, E2 represents the expected count, and so on. So in order to actually find the expected counts, so EI, all you have to do is take the number of trials, which is n, and multiply by the probability that's associated with it. So again, you just take number of trials, multiply by the probability, and that gives you your expected count. So let's take a look at this example. So a sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is any different today than it was in the year 2000. According to the U.S. Census Bureau, in 2000, 22.8% of grandparents have been responsible for their grandchildren less than 1 year, 23.9% of grandparents have been responsible for their grandchildren for 1 or 2 years, 17.6% of grandparents have been responsible for their grandchildren 3 or 4 years, and then the remaining 35.7% of grandparents have been responsible for their grandchildren for 5 or more years. So if the sociologist randomly selects 1,000 caregiving grandparents, we want to compute the expected number within each category. So all we would need to do is look at the probabilities. So we've summarized them here. Probability of less than 1 year, 0.228. Probability of greater than or equal to 5 years, 0.357, and so on. So in order to get the expected counts, all we take is n, which is our 1,000, and multiply by the corresponding probability. So for example, since we're taking 1,000 people and the probability of finding a grandparent who's cared for their grandchildren for less than 1 year is 0.228, we just multiply these two and we get an expected count of 228 out of our 1,000 people that we would expect to be caring for their grandchildren for less than 1 year. And then you get 239 and so on. All of these should add up to 1,000 since that is your total. So in order to find the test statistic for the goodness of fit test, we're going to let OI represent the observed counts of a category, and EI, which is like what we just calculated, is going to represent the expected counts. K represents the number of categories, and N represents the number of independent trials. So our formula is as follows. Our chi-squared statistic is found by taking our observed minus our expected and squaring that difference, and then dividing it by our expected. And we have to do that for all i's from 1 all the way up to k, and then we sum those all up. Now this is going to follow a chi-squared distribution with k minus 1 degrees of freedom, provided that a couple of things have to be true. All of our expected frequencies have to be greater than or equal to 1, so all of our EI's have to be at least 1, and no more than 20% of the expected frequencies are less than 5. So we can't have a bunch of very small groups. So there's a cautionary note here. Goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. If you want to compare 2 or more populations, then you have to use the test for homogeneity, which is presented in the next section. So let's look at what a hypothesis test for the goodness of fit test might look like. So if we want to test a hypothesis, we have to determine always the null and the alternative first. So the null hypothesis is going to be that the random variable follows a certain distribution, and the alternative is going to be that the random variable does not follow the distribution in the null hypothesis. Then you decide on a level of alpha, which is typically given, but it's dependent on the seriousness of making a type 1 error. And then what you need to do is you need to calculate all of the expected counts, just like we did with that grandparent one. Verify that all of the requirements are met, so you need to make sure that the expected counts are all at least 1 and that no more than 20% of them are less than 5. And then there's a cautionary note here. If the requirement in step 3B are not satisfied, one option could be to combine 2 or more of the low frequency categories into one category, and then you could still run the test. And then if we're using the p-value approach, you just compute your test statistic by taking the observed minus the expected, squaring that difference, and then dividing by the expected, and then you sum that up for all of your categories. Then you go to table 7, which I think is a table we have not used yet. This is our chi-squared table, to obtain approximate p-value by determining the area under the chi-squared distribution with k-1 degrees of freedom. So you're going to be looking for your chi-squared value, and the p-value is going to be the area to the right. If our p-value is less than alpha, then we reject our null hypothesis, and then we state some kind of conclusion, meaning there is or there is not sufficient evidence to blah, 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 whatever scenario you're talking about. So let's look back at this grandparent scenario. All right. So we have frequencies here. Okay. Less than 1 year, 252, 1 or 2 years, 255, 3 or 4 years, 162, 5 or more years, 331. So what we want to do now is test the claim that the distribution is different today than it was in the year 2000. So step 1 is to determine the null and the alternative hypotheses. So the null hypothesis is going to be that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is the same today as it was in 2000. And the alternative hypothesis says that it is different today than it was in the year 2000. So our level of significance is going to be 0.05. The expected counts are the ones that we computed in the first example. And then what was actually done is we went and surveyed 1,000 caregiving grandparents, and this is what we actually observed. So we observed 252 when we expected 228 for the less than 1 year category. So since all of the expected counts are greater than or equal to 5, the requirements of the goodness of fit tests are satisfied, so we're going to go ahead and calculate our test statistic. So you take our 252, which if I go back for just a minute, that's our observed, and we subtract our expected, and we square it, and then we divide by our expected. And then we do this for all 4 categories. So we have 331 and 357 as our last ones, which was our last category here. 331 is what we observed. We expected 357. We square that and then divide by the 357. So we get a test statistic value of 6.605. Now, there are k equals 4 categories, so that means that we have 3 degrees of freedom. And if we actually look, we're looking to the right, the p-value, when we have chi-squared equals 6.605, is going to be found to be 0.09 approximately, okay, using some kind of technology. So since the value of 0.09 is greater than the level of significance of 0.05, we're going to fail to reject the null hypothesis. So we would say that there is insufficient or not sufficient evidence to conclude that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is any different today than it was in the year 2000 at the alpha equals 0.05 level. So we can't say that the proportion of caregiving grandparents has changed at all in terms of the distribution for the number of years. So let's move on to section 12.2, which is a new topic. This is tests for independence and the homogeneity of proportions. So objective 1 is to be able to perform a test for independence. So a chi-square test for independence is used to determine whether there is an association between what we would call a row and a column variable in a contingency table, constructed from some kind of sample data. So the null hypothesis is going to be that the variables are not associated or independent, and then the alternative is going to be that the variables are associated or dependent. So in other words, null hypothesis, variables are independent. Alternative, the variables are not independent. So the idea behind this testing is that we want to compare actual counts to the counts that we would expect if the null hypothesis were true, meaning if the variables were actually independent. So if a significant difference then exists between the actual counts and the expected counts, then that would be taken as kind of evidence against our null hypothesis. So we know that if two events are independent, this is way back from chapter 5, the probability of E and F happening is going to be the probability of E times the probability of F. This is just the multiplication principle for independent events, and we just use it to obtain the expected proportion of observations within each cell under the assumption of independence. And then we're going to multiply that result by n, or sample size, in order to obtain the actual expected count. So let's take a look at this example here. In a poll, 883 males and 893 females were asked, if you could have only one of the following, what would you pick? Money, health, or love? The responses are presented in the table below, and we want to determine the expected counts within each cell, assuming that gender and response are independent. So for example, out of our 883 males, 82 of them said that money was the most important, 446 said health, and 355 said love. So if we take a look at this, we first need to actually compute the row and the column totals, because without those we can't really get what we need. So for example, we had 128 total people who answered money, 1,020 who answered health, and 628 who answered love, which totals to 1,776. And then we know that we surveyed 883 men and 893 women, which also totals to the same total. That would be a good thing to check when you've created this. Next, we compute the relative marginal frequencies for the row and the column variables. So for example, we take our 128 that we had who responded with money, and we divide that by our 1776 to get 0.0721. We take our number of people who responded with health and divide it by the total. We take number of men divided by the total, number of women, and so on, until we get all of these relative marginal frequencies. So for example, 49% of the respondents were males, 50% of the respondents were females. 7% of the respondents responded with money, 57% responded with health, and 35% responded with love. So if we take a look at this, assuming that gender and response are independent, we're going to use the multiplication rule for independent events to compute the proportion of observations we would expect in each of the cells. So
you will no longer hear beeps until someone else joins the conference.
Okay, sorry about that, having a couple of technology issues here, but it looks like it's still recording, so I'm going to continue on. So let me kind of back up for a second. So assuming that gender and response are independent, we're going to use our multiplication rule for independent events to compute the proportion of observations we would expect in each of the cells. So if you want to grab your calculator for a minute, just so that we can check some of these, if we go back to the men and the money category, if we look at the number of people who responded with money, it was 0.0721. And we're going to multiply that by the percent of respondents who are men, which is 0.4972. And when we multiply those two, we get 0.0358. So that is what goes right here. Okay, and then we go back again. Let me move back, and we take percent of health, and we multiply that by percent of men, and we would get 0.2855. So we would get this for each of our values. So this is just using our multiplication rule. And then what we need to do is multiply by the expected proportions or we need to find the expected number by multiplying by our sample size, our 1776. So we would expect 3.58% of our respondents to be men who responded with money out of our 1776. So if we take our 1776 and we multiply by that probability, that means that we would expect 63.5808 men to respond with money. And then we can do this for each of our categories. For the ones that are more likely, you're going to have a higher number. So we would expect, say, our largest category is women who respond with health, because we have 28.88% of women responding with health. So we have 1776 times 0.2888, and we get 512.9088 as our expected count for the number of women who would respond with health. And it's important that you probably check these to make sure that they add up to the 1776, because they should. This is just an alternate formula that you can use to find the expected frequency. You can take your row total times your column total and then divide by the table total, and that will work as well. Okay, so our test statistic for the test of independence looks very similar to what we had before, where we take our observed minus our expected and we square it, divide by our expected, and then sum them all up. This is going to follow a chi-square distribution. Now, the degrees of freedom are a little bit different than what you're used to seeing. So R is going to be your number of rows, C is going to be your number of columns. So in order to find degrees of freedom, you take R minus 1 and you take C minus 1, and then you go ahead and multiply those two, and that gives you your actual number of degrees of freedom. So a couple of things still have to be true. All expected frequencies are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. So our null hypothesis and our alternative hypotheses are going to look something like this. So when we have our chi-square test for independence, the null hypothesis is going to be that the row variable and the column variable are independent. And the alternative hypothesis is going to be that the row variable and the column variable are dependent. Next, we always choose a level of alpha, or level of significance, which is alpha. We calculate our expected frequencies, which is like the example that we just did with our male and female money, love, and health. We verify that all of the requirements have been met, so all of the expected frequencies have to be at least 1, and no more than 20% can be less than 5. We compute our test statistic by taking our observed minus our expected, squaring that difference, and then dividing by our expected, and summing that up for all of our categories. And then we use table 7 again, and we determine an appropriate p-value. But this time, again, our degrees of freedom are a little bit different. We have to take our number of rows and subtract 1. We have to take our number of columns and subtract 1, and then multiply those two to get our degrees of freedom. If our p-value is less than alpha, then we reject our null hypothesis and we state a nice conclusion. So let's take a look back at this. Okay, so we have our 883 males and our 893 females who are responding to this money, health, or love question. So the null hypothesis is going to be that gender and response to this question are independent, and the alternative is going to be that gender and response are dependent. The level of significance is going to be 0.05, and we compute the expected frequencies just like we did in example 1. So for example, we're shown here that we had an expected frequency of 63.5808, when in reality 82 men responded with money. Now we can look down here to kind of see where some larger differences are. I'm trying to find where it looks like the biggest difference is. Let's see, this one's a fairly large difference. This one might be the largest. And we can see we expected 512.9088 women to answer health, when in reality 574 answered health. So since none of the expected frequencies are less than 5, the requirements are all good for the goodness of fit test. So the test statistic is found by taking 82, which if we go back for just a minute, that was our observed, minus our expected of 63.5808, squaring that difference, and then dividing. And then we do this for each of our categories and we add them all up. This is kind of being displayed a little bit funny. This should be a ... that just indicates that we're summing this for all of our categories. And when you actually do this, you get 36.82. Now we know that there are 2 rows and 3 columns, so in order to find the degrees of freedom, we do 2 minus 1, which would give us 1, times 3 minus 1, which would give us 2. So 1 times 2 just gives you 2 degrees of freedom. So if we try to find the p-value, that's going to be the area under the chi-square distribution that has 2 degrees of freedom to the right of 36.82. And that is going to be approximately 0, so it's basically off our chart. So the p-value is definitely going to be less than alpha, so we're going to reject our null hypothesis. And we can say that there is sufficient evidence to conclude that gender and response are dependent at the alpha equals 0.05 level, meaning that your response in some way depends on the gender. So to actually see the relation between response and gender, we can draw bar graphs of the conditional distributions of response by gender. So recall that a conditional distribution just lists the relative frequency of each of the categories of the variables. So if we take a look at, this is our raw data again, we had 82 men with money and so on. And we just compute 82 out of our 883 because that was the number of men, 446 out of our 883, and so on. So if you think about it, this means that 9% of our men responded with money, 50.5% of our men responded with health, and 40% of our men responded with love. These will total to 100% because that's all males. And then if we do the same thing for females, 5% of females responded money, 64% responded health, and 30.57% responded love. And again, these are going to total to 100% as well. So if we take a look at this, we have males and we have their relative frequencies for money, health, and love, and we also have females. So what you can see is that females are much more likely to respond with health than males and are less likely to respond with money. Males are more likely to respond with love than females are. Okay, so objective 2 is to be able to perform a test for the homogeneity of proportions. So in a chi-square test for the homogeneity of proportions, we test whether different populations have the same proportion of individuals with some characteristic. So the procedures for performing the test are identical to those for the test of independence. So let's take a look at this example here. So the following question was asked in a random sample of individuals in 1992, 2002, and 2008. And they were asked, would you tell me if you feel being a teacher is an occupation of very great prestige? And then the results are listed below. So they could either answer yes or no. And again, this was in 1992 or 2008 with a 2002 survey in the middle as well. And we want to test the claim that the proportion of individuals that feel being a teacher is an occupation of very great prestige is the same for each year. So the null hypothesis, which is always our statement of no difference, is that the proportion for each year who feel that being a teacher is an occupation of very great prestige is going to be equal. And if we want to state that, all we'd have to say is that P1 is equal to P2 is equal to P3. And then the alternative is that at least one of the proportions is different from the others. So it could still mean that P2 is equal to P3, but maybe P1 is different or something like that. Now the level of significance is going to be 0.01. Our expected frequencies are found by multiplying the appropriate row and column totals and then dividing by the total. And these are given in parentheses. This is just like the example that we did with our grandparents, so you could look back at that one if you're not sure how to get these numbers that are in parentheses here. So this means that in 1992, we would have expected 475.554 to have responded with yes, saying that being the occupation of a teacher is very prestigious, where only 418 actually responded that way. None of our expected frequencies are less than 5, so all of our requirements are good. So in order to find the test statistic, we take what we observed and subtract what we expected. We square that, and then we divide by the expected number, and then we just add them all up. And again, this is displaying as an L right now. This should be like a ... that indicates that we're doing this for all of our groups. And when you actually do this, it's going to take a little while, but you're going to get 24.74. Now we know that there are 2 rows and 3 columns, so in order to find the p-value, we need to know degrees of freedom. So we take 2 minus 1 and multiply by 3 minus 1, so we get 2 degrees of freedom. And then the p-value is going to, again, be approximately 0 because we have a chi-squared statistic of 24.74. Now our p-value is definitely going to be less than alpha, so we're going to reject our null hypothesis. And we can say that there is sufficient evidence to reject the null hypothesis at the alpha equals 0.01 level of significance. We conclude that the proportion of individuals who believe that teaching is a very prestigious career is different for at least one of the 3 years. Now it could be different for all 3 of them, or it could just be one that's different. And we could, for this example, look at another bar graph, just like we did for the male, female, money, health, love question to see where that difference might lie. Okay, let's take a look at section 12.3, which talks about testing the significance of the least squares regression model. So we know that our least squares regression model looks like this, where we have yi, which is the value of the response variable, is equal to beta 1 xi plus beta naught plus our error term. So beta naught and beta 1 are the parameters that are estimated based on sample data. Xi is the value of our explanatory variable, and EI is a random error term that has a mean of 0 and a variance of sigma squared. The error terms have to be independent, and I is going to take on values of 1 to n, where n is our sample size. So the first objective here is to just compute the standard error of the estimate. So the standard error of the estimate, or S sub e, is found using this formula. So what you do is you take your yi minus your yi hat and you square it. Now that's just your sum of your squared residuals, which we've talked about before. We've talked about minimizing the sum of the squared residuals. And then we divide it by n minus 2, and we take the square root of that. So you take your residuals and square them, sum them all up, divide by n minus 2, and take square root, and that's going to give you the standard error of your estimate. So let's go ahead and compute the standard error for the estimate for the drilling data, which we've used in many, many videos now. So if you recall, it has x, which is our depth at which the drilling begins, and then we have our y, which talks about how long it takes us to drill 5 feet. So using technology, we found the least squares regression line to be y hat equals 0.0116x plus 5.5273. Steps 2 and 3 would be that the predicted values as well as the residuals for the 12 observations are given on the table of the next slide. So we have here, we have our x's, we have our y's, we have our predicted y's, which are our y hats, and then we have the residuals, which would be found by taking y minus y hat. So for example here, 5.88 minus 5.9333, and we get negative 0.0533. We square that value, and these should all be positive since we're squaring them. And for example, for this one, you get 0.0028. Then you add those all together to get the sum of the squared residuals, and it ends up being 2.7012. So if we want to find the sum of the squared residuals, we take our 2.7012, if we want to find the standard error of the estimate, we take the sum of our squared residuals, which is 2.7012, and we divide by n minus 2, which would be 12 observations minus 2 to give us 10. We divide these two numbers, and then we take the square root, and that gives us the standard error of the estimate, which in this case is going to be 0.5197. So now let's look at how we can verify that the residuals are normally distributed. So all we would actually have to do is just create a normal probability plot of our residuals. And you can see that these bands here, all of our points are within these bands. This is our normal 95% confidence interval, so this one looks good. Now let's take a look at how we can conduct inference on our slope. So we can conduct a hypothesis test regarding beta 1. So to test whether two quantitative variables are linearly related, we can use the following steps. Now, a couple of things have to be true. The sample is obtained using simple random sampling, and the residuals are normally distributed with a constant error variance. So Step 1, after we've determined if that's true or not, is to determine the null and the alternative hypotheses. So it can be structured one of three ways, like always. So we have our null hypothesis that beta 1 is equal to 0. That's always going to be our null hypothesis. And then alternative is going to be, if we have a two-tailed test, that beta 1 is not equal to 0. If we have a left-tailed test, it's beta 1 less than 0. And if we have a right-tailed test, it's going to be that beta 1 is greater than 0. And then we go ahead and we select a level of significance and we compute our test statistic. So our T naught value is going to be found by taking B1, which was our value from our regression line, and dividing by SB1. This is going to follow a student's T distribution with n minus 2 degrees of freedom, and we're going to use table 6 to approximate the p-value. So again, this should be very familiar to you at this point. If we have a left-tailed test, we're looking for the area to the left of T naught. If we have a right-tailed test, we're looking for the area to the right of T naught. And if we have a two-tailed test, we're looking for the sum of the area in the tails. And if our p-value is less than alpha, we reject our null hypothesis, and then we state a conclusion. These are the same steps as always. So one kind of cautionary note is that before actually testing beta 1 equals 0, we want to be sure that we draw a residual plot and verify that a linear model is appropriate. So let's take a look back at our drilling data. We want to test the claim that there is a linear relation between drill depth and drill time at the alpha equals 0.05 level. So we verify the requirements. We assume that the experiment was randomized, so the data can be used. We confirm that the residuals were normally distributed by constructing a normal probability plot, which we already looked at. And to verify the requirement of a constant error variance, we plot the residuals against our explanatory variable, which is depth. So if we take a look at this, there's no discernible pattern here, which is really what we're looking out for. So this looks fine. So if we want to actually solve this, then we're going to first determine our null and our alternative hypothesis. We're going to do a two-tailed test. So we're testing beta 1 equals 0 versus beta 1 not equal to 0. We're going to use 0.05 level of significance. And we know that our estimate of beta 1 is B1, and that was just 0.0116. So if we want to compute the standard deviation of B1, the calculations are over here. So we would take our xi minus our x bar, we'd square those differences, and then we'd add them all up, and we get 3006.25. And what we actually do in order to calculate our standard error of B1 is we take the 0.5197 that we calculated before and divide it by the square root of what we just found, and we get 0.0030. So the test statistic is found by taking B1, which is our value from our regression equation of 0.0116, and dividing it by 0.003, which is our SB1 value, and we get 3.867. So this is going to be a two-tailed test, so the p-value is going to be the sum of the area under the t distribution with 10 degrees of freedom to the left of negative 3.867 and to the right of a positive 3.867. So if we use table 6, we're looking for 10 degrees of freedom. The value of 3.867 is going to be between the numbers 3.581 and 4.144. And those correspond to right tail areas of 0.0025 and 0.001. If you actually look in the body of the table, you're going to find these two values, the 3.581 and the 4.144. And then if you kind of look up to where you have the bold numbers, those are going to be your p-values. So what you actually need to do with these is you need to multiply by 2 since we have a two-tailed test. So we're going to get 0.005 and 0.002. Our p-value is going to be somewhere between these. Now we don't know what it is, but it's definitely less than alpha, so we're going to reject our null hypothesis. So we can say that there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that a linear relation does exist between drill depth and drill time. So objective 5 in this section is to be able to construct a confidence interval about the slope of a least squares regression model. So if we take a look at our formula for confidence interval, all we need to do is we need to take our B1 value, okay, which was the slope from our regression equation that we created, and then we add and subtract our critical value multiplied by S of E over the square root of the sum of xi minus x bar squared. T alpha over 2 is computed using n minus 2 degrees of freedom. One kind of note here is that the confidence interval formula for beta 1 can only be computed if the data are randomly obtained, the residuals are normally distributed, and there is constant error variance. So there's no discernible pattern with the error variance. So let's go ahead and construct a 95% confidence interval for the slope for our drilling example. So we know that our requirements are met because we had already verified that previously, and we had also found that B1 is equal to 0.0116 and SB1 is 0.0030. So we're looking for 0.05 divided by 2, which is going to be 0.025. So our T of 0.025 for 10 degrees of freedom is going to be 2.228. That's our critical value. So we take our B1, which is our 0.0116, plus and minus our 2.228, and we multiply that by our 0.003 that we had already found. So you end up with a lower bound of 0.0049 and an upper bound of 0.0183. So that means that we're 95% confidence that the average increase in time that it takes to drill an additional 5 feet at which the drilling begins, takes to drill 5 feet for each additional foot of depth at which drilling begins, is going to be somewhere between 0.005 and 0.018 minutes. Okay, now this last section is section 12.4. We're going to talk about confidence and prediction intervals. So the objectives are to be able to construct a confidence interval for a mean response and construct a prediction interval for an individual response. So confidence intervals for a mean response are intervals that are constructed around a predicted value of y at a given level of x, and they're used to measure the accuracy of the mean response of all of the individuals in the population. Now, prediction intervals for an individual response are intervals that are constructed around the predicted value of y, and they're used to measure the accuracy of a single individual's predicted value. So let's start with objective 1, which is to be able to construct confidence intervals for a mean response. So a confidence interval for the mean response of y, or y hat, is going to be given by the following. So we have y hat, the mean response of y, is going to be given by a lower bound of y hat minus t alpha over 2 times s of e times the square root of 1 over n plus our x star, where x star is the given value of the explanatory variable, minus x bar squared divided by the sum of the xi's minus the x bars squared. So this is very, very messy, but make sure we just pull apart all of the information we need. We can use technology to help us through some of this stuff. I would check with your instructor to see if something like this is required on the final exam, and if so, how best to do these calculations if you have a large number of observations. I would assume that that's not the case, but I'm not completely sure. So let's take a look at constructing a 95% confidence interval around the predicted mean drill time to drill an additional 5 feet, starting at a depth of 110 feet. So the least squares regression line is given by this right here, which we've talked about not only today, but we've also talked about it in other webinars here. Okay. So to find the predicted mean time to drill 5 feet for all drilling starting at 110, what we do is we actually plug 110 into our regression equation, and you get a y hat value of 6.8033. Now, if you recall from earlier, S of E was the 0.5197, X bar was the 126.25, and if we summed all of the Xi's minus the X bars squared, we got 3006.25. And it's also important that we look up our critical value. T of 0.025 for 10 degrees of freedom is going to be 2.228. So this is all information that we had found in previous places today. So all we need to do is we need to take our 6.8033, which is what we got when we actually plugged in our 110 into our equation, and add and subtract our critical value of 2.228 multiplied by the 0.5197, multiplied by the square root of 1 over 12 plus 110 minus 126.25 squared over the 3006.25. Now, you need to be very careful when you're putting this into your calculator because it is very easy to mess up. My suggestion would be to kind of follow order of operations, so work your way out from the inside, and you could do this in pieces if you need to. But you should get a lower bound of 6.45 and 7.15 for your upper bound. And they should both be the same distance from this mean here of 6.8033. So that means that we can say that we are 95% confident that the average time to drill 5 feet for all drillings starting at a depth of 110 feet is going to be somewhere between 6.45 and 7.15 minutes. Okay, now let's look at objective 2, where we create a prediction interval for an individual response about y hat. So a prediction interval is going to be given by the following equation. So for the lower and the upper bounds, we take our y hat, and then we add and subtract our critical value multiplied by S of e times 1 plus 1 over n plus our x star, where x star is the given value of the explanatory variable, minus our x bar squared, divided by the sum of the xi's minus the x bars squared. So let's construct a 95% prediction interval about the predicted time to drill 5 feet for a single drilling starting at a depth of 110. So we know all of this information that we need in order to actually create our prediction interval. So then we just use our formula here. So we take our 6.8033, we add and subtract our critical value multiplied by our S of e. If we look back here, we have all of these values laid out here. And then we have 1 plus 1 over, if we look back at our formula, 1 over n plus our x star, which is our 110, minus our 126.25 squared over that sum of the squared, let me make sure I don't mess this up. Yeah, sum of our xi's minus our x bars squared. And if we do all of this, we get a lower bound of 5.59 and an upper bound of 8.01. So that means that we are 95% confident that the time to drill 5 feet for a random drilling starting at depth of 110 feet is somewhere between 5.59 and 8.01 minutes. So this is just for any random drilling that this will work. All right. So that is it for this week. I hope that this has helped. I hope you have a great rest of your week, and please stay tuned next week for a final exam review.